Hi there, welcome back to this channel. In this video, we are going to continue our electromagnetism series, and you already know that electromagnetism is composed of two subfields, which are electricity and magnetism, right? In the aspect of electricity, we have the aspect that studies another subfield that studies charges at rest, and one that studies the one that studies charges at rest we call electrostatics, and one that studies charges and moving charges we call current electricity or electrodynamics. So today we are going to be talking about electrostatics, which is the aspect that studies charges at rest. The word statics there means stationary, means in a position, in one position, not moving. Exactly. And from the word electro, that is from the word electricity. Okay. All right. So basically, we are going to be talking about charges then. Charges. And since we'll be talking about charges at rest, I want to first understand what charges are. I want to then understand how charges are, how they interact with one another in nature. Okay. So, and this will help us to understand the concept of how matter itself, in fact, is the electrical nature of matter. Yes, that's what I want to say. The electrical nature of matter. Okay. So now what are charges? Okay, now charge is one of the intrinsic properties of matter. Now, you see, just like mass is intrinsic to matter in mechanics. So when we're studying mechanics, we'll say mass is an intrinsic nature of matter. Just like that, we have charges are also intrinsic nature is an intrinsic nature of matter. Okay, so when we get to properties of charges, you are going to I'm going to clear a misconception, and the misconception is the fact that mass and charge are non-reducible to each other. You can't reduce one to the other. You can't reduce one to the other, basically. So mass charge is analogous to mass. So charge in electricity is analogous to mass in mechanics. Charge is an intrinsic nature. That is, every matter is comprised of what? Of charge. Every matter has a degree of charge, an electrical nature. Okay, so in about 600 BC, Thales of Miletus. Just to go down the historical lane, we have Thales of Miletus in 600 BC had already observed that when you rub a piece, when you rub pieces of materials together, basically amber or materials, those materials become attractive. They could attract substances. In fact, it was such that people who could do those things were called magicians, and they called them electricians. Electricians, for which is the word I mean, people that made things to attract to each other. Exactly. So, and in those days, they used it to perform these arts, and it was thought to be for the fun of it, without understanding how that it was one of the fundamental forces of nature, right? So, theories of Miletus had already found this out, and it was not until the 17th century before we began to understand what was the actual nature of matter, the essential nature of charges, rather, of charges. So it will happen that in 1745 and between 1706, and that was when Benjamin Franklin was, during the time Benjamin Franklin was alive. Um, Here in 1745, we had a particular scientist named Dufay, and within this period, we had Benjamin Franklin, an American physicist. Franklin. So they would suggest that there were two types of charges. So in fact, according to Benjamin Franklin, it was such that the charges were more like fluids that every substance possessed, okay? So that when you rub, for example, a glass rod to silk, so if you rub glass rod and silk together, the glass rod will get a positive charge, the silk would get a negative charge. But on the other hand, if you rub a rubber rod with 4, the rubber rod will get the negative charge this time, while the 4 will get the positive charge. So and it was also discovered that if you rubbed that 4 on, or maybe that silk that got the negative charge, if you rubbed it on another material, such as a metallic sphere, the glass rod will be attracted to that metallic sphere, meaning that it has passed on the charge that it held on to. So basically, charges, it was discovered that charges were of two types, okay? Or the fluid that matter had in them that they conducted was of two types, and they were positive and negative. They were positive and negative. All right. So now, it was not until later that we actually knew that what was moving, the charges that were actually moving, that were being transferred, was actually the negative charge. So then we now name the positive charge proton and the negative charge electron. The positive proton, the negative electron. All right. In order to understand how this process takes place, we have to understand matter on the atomic scale. So matter and charges, or in the atomic scale now. Now, we know that atom is made up of 3 fundamental charges, right? 2 fundamental charges or 3 fundamental particles. 2 charges or 3 fundamental particles. And what are the 3 fundamental particles? They are the protons, electrons, and neutrons, okay? So protons are positive charges, electrons are negative charges, and neutrons are neutral, yeah? And in the nucleus of the atom, we have the proton and the neutron. But the electron, you have the proton and neutron, okay, in the nucleus. But the electron moved around the nucleus in different orbits, okay? So these electrons are the ones that are mobile, that are exchanged between matter. So it is such that materials are classified into 3 based on the availability of electrons on them. And what I mean by the availability of electrons, that is, there were 2 forms of electron. There were the bound electrons. They were found to be bound electrons and free electrons, okay? So substances will now be classified into 3 based on this, okay? So we had the conductors. Now, what were they conducting? They were the ones that, according to Benjamin Franklin, were able to conduct that fluid. And we had the ones that could not conduct, which we call the non-conductors or insulators. Insulators, named because they were able to insulate us against the powerful amount of charges that some bodies conduct. Then the third are the semiconductors. Semiconductors stand in between the conductors and the non-conductors in their property. All right, so by the time I re-explain this, you are going to understand it very well. Now, the electrons were the things that actually were the charges, particles that actually moved or were exchanged between the bodies. Take an example of the silk and glass rod that I mentioned the other time. So if you rub glass rod and silk together, so the silk material is being rubbed on the glass rod, what is happening is that on the body of the glass rod, there are charges. On the body of the silk, there are charges, okay? And the charges balanced out each other so that body, initially before they came together, they were both neutral bodies. But after rubbing them together, they underwent a process known as conduction. And because of that, by the action, friction, not conduction. They underwent a process known as friction, which is rubbing against each other. So, by that action, there was a transfer of one charge from one body to the other. So, it was such that the one that had the excess of free electrons was the one that gave to the other. Exactly. Electrons moved from one to the other. So remember, I said when you rub glass rod and silk together, so the glass rod will become positively charged, the silk will become negatively charged. Negatively charged. So what happened? And we know that the negative electrons are the negative charge. This way we write the electrons are negative, these ones are positive, this one's neutral. Okay. So now what happens is this. I said the ones that move is actually the electrons. It is actually the electrons that move, and they are the free electrons, right? Okay. Now, these free electrons, we actually move from the silk, they will move from the glass rod rather to the silk. Okay. Now listen to how the process occurs. So it is such that the silk has initially has equal number of protons and positive charges and negative charges. Positive charge and negative charge. Then the glass rod also has equal number of positive and negative charges. But on contact, on frictional contact, what happens is that this guy, the silk, is going to, the glass rod is going to lose some of its electron to the silk. The silk will grab on some of the free electrons that were available, excess electrons that were available on the glass rod, and to itself, so that this guy will now have more positive charges than negative charges. So because of that, we say it has a net positive charge, and this guy is going to have a net negative charge. Okay, so that's the way it happens. So this guy that has so based on that, we now categorize substances across conductors, non-conductors, and semiconductors. Now, substances that can that can allow electricity to pass through them, or that has abundance of these free electrons, they are called conductors. While substances that do not have abundance of these free electrons, and in fact are very hard to get to charge them, they are non-conductors. While semiconductors are just in between the conductors and the non-conductors, like I said before. So an example of conductors are generally metals. They have a lot of free electrons, and that is why we call them mobile electrons. So that is why they are good conductors of electricity. And that's why when we want to charge conductors, we can charge conductors in either of these two easy steps, either by conduction or friction, conduction or induction rather, while we charge non-conductors by friction. So we charge conductors by conduction or induction, and we charge non-conductors by friction. So how do we charge non-conductors by friction? It's simply by rubbing against each other, right? So we say friction or rubbing. So after rubbing, some electrons that are available on the one that has more free electrons is going to rub onto the other, and that one will have higher negative charges than it had initially. Remember, before charging, they had equal number of positive and negative charges, so which made them neutral. So by the time they now get to be rubbed onto, one will get excess electron, the other will have low number of electrons, and what will happen is that they become charged. Okay, now take note that even though we are saying when we have more electrons, the other will have negative, the total number of charges that were in the beginning will be the same amount of charges that will be at the end, even after rubbing against each other. And so that shows you that charges are conserved. When we get to the property of charges, we are going to talk about that. Okay, now then we have conduction. Conduction is basically charging by contact. So there is a charged body which is a conductor. Is able to conduct the fluid, right? According to Benjamin Franklin, that is. So this guy can conduct electricity and is charged. This guy can also conduct electricity, but it's uncharged. It still has equal number of positive and negative charges. What happens is the moment you bring this guy to touch this guy, immediately it touches it. It is able to transfer its own charges to this body. It transfers its charges to this body. And how does it happen? It happens that by the time it comes on this body, the charges are going to separate. The charges are going to what? Separate. What happens is that if this guy was negatively charged and this guy is neutral, by the time this guy comes and touches it, it's going to have this guy is negatively charged. You know, the number of positive and negative here was the same. So since this guy is now negative, the moment I touch the head, I'm referring to this head portion now. The moment I touch the head, this negative charge is going to cause a charge separation such that positive charges will move towards the top and negative charges will move away. Why? Because of the law of the first law of electrostatics that says that positive like charges repel each other and unlike charges attract each other. When we get to Coulomb law, we are going to talk about this. Okay, so but the point is that these positive charges are going to, because this guy is negative, it will come, they will be attracted to each other. So it will come up and, you know, be attracted to this guy. Then the negative charges are going to separate to the other side of the material. Okay, so that is how we charge this body, by conduction. Then by induction, which is the second method of charging, is this. I need not touch this body. This body is uncharged body. This body is charged. I want to use it to charge this other body that is uncharged. Remembering that both of them are conductors. The moment I bring this guy close, only close to it, there already exists a charge separation. The same thing that occurred in conduction. Only that in this case, you see that there's no touching at all. There's no touching. Now, if you want this body to remain charged, what happens is this. The moment you bring this body here, close to it, while still being in place, whilst this charging body is still close to the body that is to be charged, then the charge that got separated will become earthed. Now, what is earthing? Now, earthing is the process by which a charge is conducted to the earth, the ground, the earth. Why? Because the earth serves as a reservoir of charges, both positive and negative charges. So you cannot overcharge the land, you cannot undercharge the land. That is why all charges can be conducted to the earth, and the earth is never more charged than it is, or less charged than it is. So that is why earthing, by earthing, the body is going to drain its charges. I already explained this in one of my previous videos. So what I will do is I will link that in the description so that we can quickly go, wrap up this discussion. So let's go to, so we already understand this. Let's go to the properties of charges. Now, what are the properties of charges? Now, what are the properties of charges? Now, the first property of a charge that you must know is that charges are conserved. Charges are conserved. Conservation of charges. Now, what does that mean? What does that mean? So if I have two bodies, so let's say I have this rod and this silk material. So if the number of positive charges here were 3 and balanced out by the number of negative charges, or were 4, and here we have only 3 positive and 3 negatives. Okay, the moment we rub this guy on this guy, this guy is going to transfer some charges onto this guy, because we said this guy will be positively charged. So it means that the negative charges will leave here and come here, isn't it? Remember that initially, let me return these negative charges. Initially, we had plus 3 positive charges, 3 positive charges, 3 negative charges. That means total charge 0, right? That's why the body is neutral. electrically neutral. This guy is also +4 and -4, so electrically neutral. The moment you rub them together, these two negative charges will fall here. Remember, it's not just negative charges, it's just my example. So on this, on account of the rubbing, what happens is that we now have 1, 2, 3, 4 positive charges and 1, 2 negative charges. So at the end of the day, what do we have? We have total charge here is going to be minus +2, I'm sorry. As we're saying, the positive charges are now 4 and there are 2 here. So by the time you sum it up, you're going to have minus +2. By the time you do the calculation here. And of course, here you have, so now we still have 3 positive charges. So we have +3. But here, negative charges has increased by 2. That will be -5. So by the time you do that, you solve that, you're going to get -2. Okay, so -2 + 2 is going to be what? 0. You remember that we started at 0, 0. All right. So you see that we did not make any new charge. So another way we can restate the law of conservation of charges is that charges can neither be created nor destroyed. So what we just did here is to add charges. Redistribute charges. What we did here is just redistribution of charges. We did not make any new charge. Is that clear? All right, so the next property of charges that we ought to know is that charges are quantized. Charges are quantized. Quantization of charges. I'm trying to make the handwriting as big as possible so that we can see it. I hope it's clear. Quantization of charges. Quantization. Okay. So what that means is that charges are quantized. And what do we mean by charges are quantized? So charge has a particular integer value. They have a particular value. Charges have a particular value. So for example, our fundamental charges rather have a particular value. So the fundamental charges, protons and electrons, which are equal but opposite, have the value of 1.6 times 10 to the power -19 Coulomb. That's the charge. For electron, is going to be negative this. For proton, is going to be positive this. Okay, so anybody or any matter or any material is going to gain an integer multiple of this value. Does that make sense to you? It means that the quantity of charge on any matter is going to be an integer multiple of either positive charge, negative charges or positive charges. But this is the way we write it to identify or depict the fact that it is negative charges that are actually moving. That's the way we write it. So charges are quantized, okay? That every matter will gain an integer multiple of a quantity of positive or negative charges. All right, let's go to the third one. Another property of charges that you should know is the fact that charges are relativistically invariant. Charges are relativistically invariant. I have covered the topic of relativism in a former video. So what I will do is I'll link that video in the description. What I mean by it is relativistically invariant is the fact that no matter the scale you are talking about, a charge is positive and or negative. Is that clear? Charges don't change at an atomic scale or on the relativistic scale. For example, in relativism, where we talked about masses, we saw even for time, We saw time dilation and expansion. We also saw how masses can also change due to um, you know, that those values are quantities rather are actually relativistic. That is, it depends on the scale of frame of reference. It depends on the frame of reference. But with charges, in all frames of reference, it is the same. Whether it is positive, it is always positive. If it is negative, it is always negative, regardless of the frame of reference. So it is relativistically invariant. Another thing is that charge, a charge or charges are fundamentally scalar. They are fundamentally scalar quantities. That is, they have magnitude measured in coulombs, We're soon going to get to what a coulomb is. Okay. Then, so they are scalars, meaning that they have only magnitude but no direction. Charges cannot exist without masses. Charges cannot exist without mass. But otherwise is true. Or the reverse, rather. But reverse is true. What this means is that masses can exist without a charge, but a charge cannot exist without mass. Now let's get to the Coulomb's law then. Now, Coulomb was the scientist who, in 1785, gave us the force of gave us the description of the force between two charges in space. Okay, that he showed us the force of attraction or repulsion between them and how to calculate this force, the nature of the force and how to calculate it. All right, his name is Charles Augustine de Coulomb. Charles Augustine Auguste. Well, I think Augustine is the modern, so Charles Augustine de Coulomb. So in 1785, he gave us two laws, which are the fact that like charges attract and like charges repel, and unlike charges attract. Okay, then the second one is the one that tells us how to calculate the force of attraction or repulsion that exists between charges. So you can already see that the charges my experience experience repulsion or attraction. Okay, so and that one says that the force of attraction between two charges, name two charges Q1 and Q2, is directly proportional to the product of the charges, but inversely proportional to the square of the distance between them. Directly proportional to the product of the charges Q1, Q2, but inversely proportional to the square of the distance between them. So by introducing my equality sign, we have K, F equal to K, Q1, Q2 over R squared. Okay, this is the scalar form of this force, of this expression. This is the scalar form. And you can already see that it is analogous to Newton's law of universal gravitation, because it looks like it. Since this one was proposed before that, I saw a meme some time ago on the internet that Coulomb, it was a meme on Mr. Bean copying in an exam. He was copying someone, and the moment the person caught him copying him, how do you say that? Mr. Bean was copying another Mr. A. So Mr. A caught Mr. Bean copying him, and Mr. Bean looked away as though he were not copying. So that Mr. A was referred to as Newton, and Mr. Bean was referred to as Coulomb. So we call both laws inverse square law. And it is because it has that inverse square law has a particular impact on the force itself. That mathematical relationship has plays a very big role. It's not the subject of discussion for today, so but just know it is also called the inverse square law. So the point is this: they look alike. The difference is that this is the force of attraction between masses. Okay, this is the force of attraction between masses. And now it could spur you to thinking about how that masses only attract each other, never, even though masses masses have charges on them, and the masses are not repelling each other, while all the time, so all the time masses attract, but charges are either capable of repelling or attracting each other. The force, electrostatic force, which is there, is either attractive or repulsive. That's my point. It's either attractive or repulsive. All right, so these are the two forces. Now, let's get on to the mathematical aspect of this thing now. So this force, this tells us that the moment you double the distance between them, what happens is, if you double the distance between them, mathematically, if R, let's take R to be R in the first case, and we double R, by the time we double R, R becomes 2R. Does that make sense? Our new R becomes 2R. New R. Okay, so initially F was KQ1, Q2 over R squared. Okay, the new guy becomes F. By the time we double this, F will be equal to F will be equal to Q1. So this was initial, this is the second F. KQ1, Q2 over R. Now, the R is now 2R, so that becomes 2R all squared. Okay, by that we have F2 equal to KQ1, Q2 over 4R squared. Okay, what does that tell you? It tells you that the value of this guy is going to reduce by 4 times. Sorry, it's not half. It's going to reduce by 4 times the value of your force. The value of the force that will be felt will reduce by 4 times if you double the distance. So double the distance. So this mathematical equation tells us that exactly, that if you double the distance, comma, force here, F, reduces by 1/4. Exactly, reduced by 1/4. And that makes sense because this was what we got before. By the time you put that here, remove 1/4 times KQ1, Q2 over R squared. This is that. So it's 1/4 of that, of F1. 1/4 of F1. You know this is F1, right? So that is that. If you double R, this other guy will reduce by 1/4. Okay, so that's that. Let's get on to the scalar and vector notation of this. No, first let's discuss the constant of proportionality there. So there is the Coulomb constant, and they are of 2 types. First, this Coulomb constant K is given by 9 times 10⁻⁹ Newton per K becomes Newton meters squared per Coulomb squared, okay? So experimentally, it was discovered to be given by the formula 1 over 4 pi epsilon naught. Now, you see, epsilon naught here is permittivity of free space. Okay, now what this tells you is that it is dependent on that the force is dependent on the permittivity of the medium, permittivity of the medium. What does that mean? It means is there how much the medium allows for the attraction or repulsion, how much the material allows for electrostatic force to actually act. That is what we mean by permittivity there. So there is permittivity of medium and there's permittivity, relative permittivity. I'm going to get into this in just a few moments. Now, this one has experimental value of 8 times 8.5 times 8.85 times 10 raised to the power minus 12. That is the value of epsilon naught, which is permittivity of free space or vacuum. Free space or vacuum, okay? So, but permittivity of a medium, so the value of K depends on the permittivity of a medium, okay? So the small k, we use it to refer to permittivity of free space. But because students usually get confused, there's small letter k and there's big letter k. Exactly. The capital letter K is the one that we use when we talk about permittivity of a medium. Now, relative permittivity is actually given by the permittivity of medium. This one we said is permittivity of medium. Okay, so the relative permittivity is given by the permittivity of a medium over permittivity of free space. So if we want to calculate for permittivity of a medium, it will be permittivity, relative permittivity times permittivity of free space. So that, in other words, we are saying that if our equation here became F equal to, by the time we introduce this value of K in here, we have 1 over 4 or Q1, Q2 over 4 pi epsilon naught R squared. If this is the case, then it means that when we are talking about a different medium than free space, if we are talking about a different medium, then our force of attraction or repulsion is going to be equal to Q1, Q2 over 4 pi epsilon R epsilon naught R squared. I hope this makes sense to you. I hope this makes sense to you. Permittivity of medium with permittivity epsilon R being permittivity of relative permittivity. Okay, and epsilon naught being permittivity of free space, which has this value. Okay, and with that, the constant becomes capital K, but either way. So these are all scalar forms of the equation, the scalar forms of the equation. Now let's talk about the vector form of the equation, or vectorial form of the equation. Now please just stick with me, because this is where students get confused, or the part that they don't like, and it's just simple. It's just maybe the way they study it. It's not, they are not studying the right way. Now in the vectorial form or vectorial notation, first know this. Our notations, okay, maybe I should first explain the notations for us so that we can understand the differences in the notations that we use. So now there is this, which means unit vector, R cap, R cap. Then R with an arrow is a position vector. Now let me put equal to, so that position vector. Okay, now unit vector is just a vector that has magnitude of 1. It has a magnitude of what? Of 1. And it only tells direction, tells or gives direction. There's nothing it's doing there. The value in magnitude is actually 1. So if I use R cap or caret to multiply anything, is the same as multiplying that thing by 1. Does that make sense? Only that now it shows a particular direction. But this guy is a position vector. A position vector. Mathematically, the relationship between unit vector and position vector is this, that R caret is going to be equal to the position vector over the magnitude of position vector. Does this make sense? So that if I take position vector from one place to another, if I give the actual direction we are going to, like from position vector between, that is from 1 to 2, it means that I'm going to take the, if I take the unit vector from 1 to 2, then it means I'm going to be taking the position vector from 1 minus that of 2. If I'm not giving a value for R, then R will be my origin, which means it will be 0 minus R2, which will be a particular value that I'm going to, the distance I cover. So this will be the actual mathematical, mathematical, like how we solve for it. Is that clear? If we want to get the position, the value of the position vector, okay? So then, this is the position vector, is that clear? Also, if you want to now solve for, the unit vector, R cap will now be equal to vector R1 minus R2, position vector R1 minus R2 over the magnitude of R1 minus R2. Is that clear? Now, in this case, we are going to have whether an I or a J. When I solve a question for you, are going to understand what I mean by that. Now, so the moment we now introduce this into the equation, so our first F vector, exactly, this arrow denotes vector. You already know that. You should at least know that. So F will now be equal to K, Q1, Q2. Remember, these are scalars. K, Q1, Q2 over, now, if I just wanted to put, if I was just talking about one position, just the distance between them, the position vector between them, that will become R. Usually they are never isolated. The force, you see, if I have a point charge here, another point charge here, call this Q1, call this Q2. You see, the force of attraction or repulsion, let's say they were both positive charge. If they're positive charge, there will be a force of repulsion. The force has a direction, is acting in this direction. The force of this is acting in this direction. Is that clear? And this force here is equal to this force in magnitude, but not in direction. Do you see that? This direction, okay? And how do we represent that in mathematics? First, there is a name. The name of this force here is going to be the force on charge 1 due to charge 2. And this one is going to be the force on charge 2 due to charge 1. You see F21, F12. F12 means force on charge 1 due to charge 2. F21 means force on charge 2 due to charge 1. So F12 will be equal but negative of F21. Does this make sense to you? Force on charge 1 due to 2 will be equal to the negative of force on charge 2 due to 1. By the time we do the superposition principle, that will not be in this video. I just want to use this video to show you how to solve questions, and we'll introduce you to it primarily. When we get to solving advanced questions, you are going to see. Okay, so Physics 102 questions, that's what I mean. Okay, so this is, you know what I mean here. So if I want to discuss this force, for example, so this is F12, that is force on charge 1 due to charge 2, is going to be the position vector that points from 1 to 2. Is that clear? the position vector that points from 1 to 2, because it's force on charge 1 due to 2, right? So it's going to be the position vector that points from 1 to 2. Is that clear? Okay, so position vector, then squared. Now, if I square it, it means that I'm multiplying with a unit, because it has a direction. It has a direction. It means I'm multiplying with the unit vector that points from 1 to 2. I hope this makes sense. The unit vector that points from 1 to 2. Okay? Now, let me introduce something else to this. Just in case you see that, I'm going to explain this, but if you already get this, then you're good to go. I'm going to, in the supervision video, I will use this to solve questions. Maybe I will even use this to solve questions in this video, but let's see. So we have F12 will be equal to, now, I can rewrite this as KQ1, Q2. Yeah, if I just want to use K, yeah. Okay. Over, now, you remember that R1, R2 was this, yeah? Okay, so I can write this as this. The magnitude of position vector R1 minus R2. Now, all cubed. Listen. Now, you know that this guy, this unit vector, has this formula here. So, if it were squared here, it means I am multiplying by this position vector, unit vector, which is position vector R1 minus R2 over the magnitude of R1 minus R2 position vectors. So by the time I multiply this, then our force on 1 due to 2 becomes KQ1, Q2 all over magnitude of R1 minus R2 all cubed. Dot R1 R2. So this is another way we can express, this is the vectorial notations that we can have for. Another vectorial notation is just introduce this relative permittivity and all into this equation. Then this can become F1 due to 2 will be equal to Q1, Q2, position vector R1 minus R2 all over 4 pi epsilon R epsilon naught R1 minus R2 cubed. Okay? So these are the possible notations, possible vectorial notations that you can have for the Coulomb's law. So with all of this said, let me look for one question for us to solve, or two. Let's solve one or two questions. Of this question, it says two similar balls of mass M are hung from silk threads of length L. So two similar balls, they are hung from silk threads, of length L, and carry similar charges. So if they carry similar charges, they will repel. Prove the separation. Okay, the separation between them. So if they are hanging, it means that the right solution here. So it means that they're hanging from somewhere, right? One is hanging in this direction, the other will hang in like this direction. Okay. So the distance of separation is what we're proving here. There's an equilibrium position here, or like the middle there. And the length of this thread here is LL. Okay. So since we already have a triangle, a right angle triangle here, from here to here, wait, let's see if we need it. It says, prove that the separation X is equal to this. So you can see in this equation what looks like Coulomb's law here. So what Coulomb's law we apply here? Since they are similar charges, Coulomb's force of repulsion, right? So the force of repulsion between them will be equal to KQ1. No, we don't need K, right? We need the actual value. That will be Q1 Q2 over 4 pi epsilon naught r squared. R in this case is x squared, yeah? Okay, and since the charges are the same, it will be Q squared, not Q1, Q2, Q squared. Okay? So if this be the case, this is the force of repulsion. Okay? Two similar balls of mass, these are on from 6 threads. Okay? Oh yeah, let's equilibrate it. It says when theta is small. So it means this is our theta, the angle at which they are, being displaced. So at equilibrium, it means at equilibrium is the point where there is maximum force of repulsion pushing them apart here. So what is that force doing? The force is acting in this direction. Does that make sense? The force is acting in that direction. And that force that equilibrates it, that force is going to be equal to, these are balls, right, that have masses, mass m. And recall that mass acts vertically downwards, right? So if that is the case, if there is a force acting in that direction, a force acting in this direction is the same as a force acting in this direction, taking this place as theta using alternate angles. So a force acting in this direction here is going to be the force acting in this direction the force acting in this direction, it's going to be equal to a force acting in this direction. Yes, the force acting in this direction is equal to a force acting in this direction. Okay, so so F will now be equal to, no, let's not introduce this then. Let's make the force act in this direction. So if the force acting in this direction is going to be mg, which is weight here, yeah? The weight of the body will be mg. Since it is opening this angle, it will be mg sine theta. I have explained that before. When it is opening an angle, you use sine theta. When it is closing an angle, you use cos theta. But let's be sure, since the force is acting in this direction, is actually opening this angle here, is opening it. So mg sine theta. So this force of repulsion is one that is trying to equilibrate it, right? So it's equal to the force that equilibrates it at the end of the day. So this and this will be equal, so that we have F is equal to F of repulsion. Then what that means is that mg sine theta, mg sine of theta should be equal to q squared over 4 pi epsilon naught x squared. Good. Okay. Good. So what's our theta? Okay, theta is not given here. Okay, we can look for a value for theta since we already have a right angle triangle here. A right angle triangle system. Here is L, right? This is our right angle here. And from here to here is X. Midway is going to be X over 2. Does that make sense to you? And this is our theta. Okay, if that be the case, then sine theta, opposite already, right? Sine theta is going to be opposite over this, which is equal to x over 2 over L. So sine theta will be equal to x over 2L. I hope this makes sense. So our sine theta, which is said to be very small here, is x over 2L. So what that means is that our equation becomes mg sine theta, which is mg x over 2L. So mgx over 2L altogether. mgx over 2L equal to q squared over 4 pi epsilon naught x squared. Okay. So what are we supposed to do? Well, we are supposed to prove for x. So we should remove x, make x subject of formula. So what we will have at the end of the day is that we'll cross multiply and we'll have mg 4 pi epsilon naught mgx cube. 4 pi epsilon naught mgx cube. Does that make sense? This times this x cube, 4 pi epsilon naught mg. Okay, will be equal to 2l q squared. 2l q squared l. Okay, 2l q squared. We're getting to it. So, okay, so from here we'll now divide both sides by 4 pi epsilon naught mg. 4 pi epsilon naught mg. So this. So x cube will now be equal to, yes. Okay, 2 takes care of 4, here 1, here 2. And that's the answer. So x cube will be equal to q squared L over 2 pi epsilon naught mg. Okay, then to make x, if you don't want to make x subject, I thought it was actually harder than that. If you want to make x subject of formula, then you take cube root of both sides. So if you take cube root of both sides, cube power will cancel cube root, and x will be equal to q raised to power 2l over q squared l over 2 pi epsilon naught mg, all raised to power 1 over 3, which is cube root. All right, so that is the proof for this one. And I hope that is clear. Okay, the second one looks quite simple. It says two spheres charged with equal but opposite charges. So if they are equal but opposite, that's attraction, right? The full force of attraction. Two spheres charged with equal but opposite charges experience a force this. The force of attraction that they experience is equal to 103 Newton. When placed 10 meters apart, the distance r between them is 10 centimeters rather apart. So 10 centimeters to meter, that will be 0.1 meters. You divide by 100. You must convert. I probably didn't mention it. So you must always convert from centimeters to meters. Apart in a medium of relative permittivity 5. A medium that of relative permittivity 5 E sub r. One thing I probably did not tell you is the definition of Coulomb. And the definition of Coulomb is that a Coulomb of charge is the quantity of charge that experiences this amount of force when placed exactly 1 meter away from another charge which is equal in magnitude and when it is placed in 1 meter, when it is placed 1 meter away from a charge, from a similar charge. I hope that makes sense. Anyways, you don't need definition. It's just for you to know that this is very, very important that you convert. Okay? So that's relative permittivity 5. Determine the charge on each sphere. Determine the charge on each sphere. We're going to need our calculator here. So we already know this. Recall that F is Q1, Q2. Since the charges are similar, it's equal but opposite. So we can just say Q squared over KQ squared over, no, we're not using K here now. We're using epsilon naught. So we need epsilon naught, which is 8.85 times 10 raised to the power minus 12 Newton meter. I didn't give the unit of that one. You can already use that mathematical relationship to get it. It's simple. So this guy, epsilon naught. So it says that it's placed in a medium. So we are using permittivity of medium now. Is that clear? There are two things you could do. You could either solve for the permittivity of medium, which will be equal to permittivity of relative permittivity dot times permittivity of medium. Relative to permittivity times permittivity of free space, or use the formula directly. So I want to use the formula directly, and that formula will be F, as I said, you should recall, equal to Q squared over 4 pi here, epsilon R dot epsilon naught R squared. Does this make sense? I could already solve this, then introduce it in the equation, but I just want to use it directly. So Q squared is what we're looking for, right? Q is what we're looking for. F is already given. So we have 103 is equal to Q squared over 4 pi dot E sub R, which is 5 times E sub naught, which is this, 8.85 times 10 to the power minus 12 times 0.1, 0.1 all squared. So Q squared will be equal to 103 times 20 times this will be, okay, by the time you do this, 0.1 times 0.1, 20 times this, 2 times this, 0.2. That becomes 0.2 times pi times 8.85 times 10 to the power minus 12. Okay, so if this is the case, then Q will be equal to the square root of everything there. So let's multiply that. That's 103 times 0.2 times 8.85 times pi. This gives us square root of 572.7437. Let's just stop here. 43. Then times 10 to the power minus 12. The square root of this will be this times 1 over 2. I hope that is clear to those of us that, I hope that is clear. So the square root of this is going to be 23. Q will be equal to 23.93 times 10 to the power minus 6. So in standard form, Q becomes 2.393. Yeah, 93 times 10 to the power minus 5. All right. So that will be the answer to that question. In our video on superposition principle, I'll be solving more questions. This video is already long. I will solve more questions. That one will be simply for questions before we go to electric fields. And make sure you watch all this series. I promise you, by the time you watch all this series, you can't have any problem with your exams in Physics 102. Do well to subscribe to the channel and share the video with your friends. God bless you.